All right. Hello, everyone, and welcome to another episode of working on Vectrexy, my Vectrex emulator. Today, I'm going to just continue, where I left off. That is to say, I have more CPU instructions to work on, so I'll just keep working on that. Last episode, when I was working on this, I added these descriptions to each of the instructions, which I was able to extract from another file. And this allows me to just have this helpful, when I'm debugging, it allows me to see over here on the right side what this instruction means. I mean, I know a good chunk of these now, of course, having implemented them, but every once in a while, I kind of forget, and I think it's helpful for people on stream also to be able to kind of figure out and learn at the same time this instruction set while I work on it. So yeah, that's pretty much where I am. There was one other cute little feature I thought I might implement. I'm not sure if I'll do that today, but at some point in the debugger, it's because usually when I start debugging, I have a few things I like to do, like I always find myself having to type this like load symbols, and I like to load the symbols from this file. And I know that sometimes I need to, let's say, set up some addresses. Like right now, what I do is I set this address here, the value of this address to FF. So these are two things I need to do every single time I launch. So I was thinking of having some feature like kind of like a load script, like an auto load or auto execution script, where when the debugger starts, it just executes lines from that file, and then that would avoid me having to do this. I also thought about kind of another way around that is if I could save off the history of all the everything I type into the console here, like everything I type into the debugger, if I could save it to a file, this history, and reload it, that would be cool, except that I'm taking advantage of the way the Windows console works, and it already does support this kind of like history thing, but it doesn't survive past the run. And I mean, this is the same thing like if you bring up a command prompt, in Windows, the things that you type are there for this session, but if you kill the prompt, it doesn't remember it. So that's sort of the situation here. And I kind of quickly looked at what it would take to do my own history, and I would need to basically override the existing system. So maybe that's something I'll look at eventually. But for now, this is pretty good. So I'll just run until I get the next instruction that doesn't run. It's interesting because you see, like, it's not going as quickly as last time, and the reason for that is this actually takes quite a bit of CPU processing power, and it's what I noticed is that it competes with OBS, which I'm using to record the stream, and what was happening was when I would run through this, OBS would start to stutter and my stream would stutter. But now instead I gave OBS higher priority, so no more stuttering on stream, but in return I get this kind of like, the execution is a bit slow. So maybe at some point I need to look at why it's taking up so much CPU. I think it's extremely suboptimal what I'm doing when I'm disassembling tons of string allocations and all that. I mean, I don't really care that much, but maybe I have to optimize it just a little bit. But for now, it's fine. At this stage in the emulator, it's perfectly fine. So basically, I'm failing on NOP, no operation, so that should be fairly trivial to implement. So let's work on that. So actually, I wanted to take note of what instruction that was. Yeah. Okay. So just let that run out. Okay, here we are. So it is at F4 AC. Let me write that down. I'll just take down the whole line. The reason why I'm writing this down is that once I've implemented it, I want to just be able to run until this in this address, and then I'll step and just see what happens after that. Okay. So NOP. It's right here. Go to CPU, so we need to put in a case for NOP. I'll just put it like right at the top here. Case for NOP, and I guess I have nothing to do because it's a NOP instruction. I don't think there's anything to worry about here. The amount of cycles for this has already been taken care of up here. And I suppose a NOP takes no cycles. Maybe it takes one. Let's see. Yeah, it takes one cycle. Let me just make sure there's nothing at all to know about NOP. What just happened? Okay. No operation. This is a single byte instruction that causes only the program counter to be incremented. No other registers or memory contents are affected. Perfect. So that's nice and easy. Let's run this. So I'm going to run until this. I'm going to have to set. This is what I mean by having to always remember the instructions that I have to set. Okay. So we just stepped over NOP. Okay, so we just keep going. Let's just continue. I think I might be in an infinite loop here. Wow, it's crazy how much slower it is. Yeah, okay. We stop here. There's definitely a repeating pattern here. See here, -6, and -6s again. Although here, no, here it's -3. Let's just keep going. Let's just see what happens. -6s again. -3. Okay. Yeah, some kind of infinite loop here. What I need to do. Hold on, I'm just going to mute my. Forgot to mute my my browser here. There we go. Okay, so let me just load symbols again. Load the symbols from here, Vectrex Inc. Just need to kind of see if I'm in a, like, where am I in the BIOS right now? Okay, so I see here, this is probably what's going on here. We're writing to the VIA port A and B and A over here. So that's probably why this isn't going anywhere, because I haven't implemented the VIA, and here it looks like we're actually writing to it, probably expecting something to happen, So let me just see if I can find where this would be happening in code. So some kind of like, we're storing we're storing A at the DP offset 0, so that ends up being D0000, so DP is set to D0, and then at the 0th offset from there, so that resolves to this address, which is the via port B. So we're trying to store A there. We're trying to clear accumulator. So we're trying to clear this via this register here, the via port A, and store B here. So yeah, basically we're doing some kind of writing to these via port registers. So let me see if I can just detect that in this here. Just gotta open the BIOS. Okay, so what am I looking for? I'm looking kind of for, I don't know if I'm looking for this load B. Maybe this will help. Or actually, yeah, look for vec text height. It's not super obvious finding your way, like kind of like mapping the disassembled output from the trace to the actual BIOS program here. So let's see if I can, oh, one thing that can help though is I do have here F4EB. Yeah, it looks like I'm actually really very much in this vicinity. F4VB is up here. Yeah, actually this is exactly where I am on the screen here. So let's see. What is this bit of code? Print string. Oh, okay, so this is the print string routine. This is the routine which does the actual printing of a string. The U register points to the start of the string. Okay, so I think what this is it might be like when we boot the BIOS, it wants to print the string on screen that says Vectrex. Like, it'd be fun if I can actually show that. Let's see if I can find that. Yeah, here. So you see this? This is the Vectrex boot up. So when you start up the Vectrex, you see that it draws these lines here, and it writes Vectrex GCE entertaining new ideas. And this is actually something that the BIOS routines handle. It has this print string, and you can control the height and the width of the characters, and it will actually do this for you. It'll control the vector beam and print out these characters in this correct way. So it's pretty cool. And we could actually probably figure out what it's trying to print right now. Because like as it says here in the BIOS routine, print string, it says that if we look at the U register, we should be able to figure out what it's trying to print right now. So let's see. I wonder if I say here info reg, so U points to F132. You know what? I don't have a way to, like, that would be super useful, is if I could like do like a kind of like a memory dump, you know, like be able to say show me memory at this address. Like I can print one P, you know, if I say P F132 like this, I'll just get like one value, 54 in hex, which is 84 in decimal. What would be really cool would be to be able to print out like a section of memory, a little bit like the Visual Studio Debugger does, and like have, let's say, a part of the screen showing the hex values, and like on the right side interpreting it as ASCII. And then we'd be able to see text that's written in memory. That would be really cool. But just for now, let me just take a look if I can if I can put a breakpoint and just use Visual Studio to take a look at what's in memory. So this U is pointing to F132. So if we go to the code and look at the memory map, F132. So where does that place us? Okay, so, oh, actually it's in the Mindstorm piece of code. Could that be correct? It's possible. It's possible. I'm trying to understand here. We're here now. Whoops. I see here load U, this value here. Okay, right. F1, which is like the first part of load user stack pointer. Because I think what happens here, okay, I guess I'm not really showing it here because loading U is loading a 16-bit register. So I'm only showing 8 bits. So this is actually not very useful. I should show 2 values in this comment section to show what really is in there. And that's why it's F132. So this must be the address that was stored at this address when this instruction was loaded. So, okay, so F132, so it looks like I said, that we would be reading a value out of the Mindstorm screen. So maybe we've passed the Vectrex part and now we're trying to load Mindstorm and display the Mindstorm screen. So like if I search for Vectrex Mindstorm, I wonder if we'll see the boot up here. Okay, so that's exactly it. That's the boot up for Vectrex. And there's Mindstorm. So I wonder if it's one of these strings. So let's see. The way to know would be to go to, where is this again? BIOS ROM. Put a breakpoint on read. And we'll do a print again of this address in use, which should hit my breakpoint. Yeah, exactly. So we're trying to read this address, 0xF132. And then I have this here. I need to take that address and map it to the range of this data buffer here. So that's what this function is going to do here. So I take this address. I assert that it is in the expected range, which it is. I subtract the first value of that range and then modulo this logical size, and then that will return the memory mapped address into this buffer. So let's go back here. I messed up my debugging windows, but that's okay. All right, so let's go to auto here. If I step out, it returned 0x1132. So if I take my data here, I wonder if I can I do this? 0xF132. No, sorry, 0x1132. T. Okay, and can I think if I do plus instead, no. Why not? What is data again? It's a array. Okay. So if I cast this to a char star in my debugger, hopefully you can read this. I know it's a bit small, the font size in here, but it's not super easy to change. So I'm casting mdata here. No. Unsigned char to char star. Okay, because that's why it's an m. I need to access ._lms. Now if I add my offset 0x1132, Look at that. That's interesting. And let's say I want to see 100 values. So basically what we have here is, and it's like the ending of the entertaining new ideas. We can see that. So this actually would be part of the Vectrex screen. We don't see it here, but we saw it over here. Entertaining new ideas. Don't quite know why maybe what's happening, oh, it must be that U is pointing to, well, it's supposed to normally point to the entire string, but maybe this routine is moving U through the string. That's entirely possible. F4, C0. I'd have to like find all the places where U is modified. But anyway, so it looks like we're in the part still in the boot up process where it wants to print this entertaining new ideas. That's kind of cool. Hey Kevin. Yeah, no, it's because you're suggesting that I try casting the address of mdata0, which might work, but the thing is that I think what we're seeing here is it's the visualizer that's displaying, so I'm not sure if the visualizer will be happy. Oh, yeah, it totally works. In fact, I think then the visualizer does some magic, right? Because in the end, this is a stood array, so you never quite know how much when the visualizer gets in the way or not, right? So yes, this really does return a pointer, so then at that point I can start adding offsets and everyone's fine. So yeah, good one. So yeah, welcome to the stream. Thanks for joining. Okay, so this is cool. So we know that it's actually trying to display this part of the string. I'm kind of like feeling like I want to add this like memory view. So that makes me wonder if I just keep running, is it always that same address? Is it moving forward, you know, bit by bit? Like if I stop here, actually if I stop at where print string would be, which is F495. So let's do that until F495. Okay, so here we are. So you can see here again, store U, info reg, F141. I already forgot what was the value we had before. Let me see here. Print F132. So we see that U is changing. So that's kind of interesting, right? So if we print F141, I'll reactivate my breakpoint in here. Step in, step out. Yeah, so it's 1141. So what I can do here is, just to make this simpler, is take mdata plus whatever address we get BIOS here. Can I access this here? Yeah. Range dot first. So subtract that. New ideas. There we go. And what's interesting to note also is that it's not null terminated. And we can see that it says that in the print string routine here, it says that the string will be terminated with 0x80, which is this symbol here. 0x80 as a character. Or not. There. I guess comma C was not the right thing. And I guess there's a null, there must be a 0 after, which is why it's null terminating it in the debugger. Okay, so I think what's happening here is that it's probably on this boot up screen. Okay, no, so let's say we passed entertaining, and now it wants to print new ideas. So yeah, let's just keep going. Let's just see what happens next. It's just like really slow. I don't know if I think what's going to happen is that it eventually will move on to the game, which would be really cool. Oh, you know what? My until, instead of doing that, we'll break on it. We'll just keep a breakpoint on it. Because until creates a temporary breakpoint, and then once we hit it, it removes the breakpoint. But I want it to kind of always hit it when we get to that print, if we get to it again. Aha! Something bad happened. What happened here? Oh, it looks like I might have a bug in. I might have a bug in my disassembly here. In my debugger. Yeah, why is this 2 and 3? I think I meant 1 and 2 here. Or what did I do here again? Post byte is 0, and post byte 2 should be 1. I guess I haven't printed many of these yet, which is why, or I've printed them but not with, this must be like the first time I printed instruction that actually needs to, I don't know what instruction it is, but let's see here. What's the opcode? Instruction. So it's doing a load B in indexed addressing mode, which is this more complicated one. Yeah, I think I just got these indices wrong. I guess because of the post byte 2 here. So actually this is 1, this is 2, same thing here. 1 and 2. Wow, so this is like all wrong. 1 and 2. Okay, just double check. And this is why it's a good thing I used standard std array rather than just like a regular C-style array, because it asserted as soon as I indexed out of bounds, which is really awesome. So I get the benefits of a C-style array with the checks that come with using std array, and also the ability to iterate and use it with algorithms. So totally a good idea. Okay. Okay, so load symbols. And set our dude register to FF. I actually wonder if I like minimize it, if it'll print faster. I don't know. Don't know what, if we're bound by, I can take a look at the CPU usage. Seems to make no difference. Or, no, actually it does. When I minimize it, OBS uses less processing power. It's super interesting. Okay, so now I got another vector subscript out of range, but in a different place. So we want to branch here, branch to F6 EC. So what's happening here? Oh, again, this is a disassemble. So maybe this is, again, part of the debugger not doing its job properly. Let's see here. So the effective address that it wants to read is 7BED, which gets mapped to the cartridge. And then when it tries to read it, vector subscript out of range. Why is that? Is this not a large enough buffer? I mean, that's what it implies. $4K. That's totally wrong. The physical size here is 32K. Why would I have put 4K? That's strange. Let me just double check. So here's my memory map again. So cartridge ROM space, physical size 32,000 bytes, so 32K, and yet when I it has a size of 4096. Let's see. Trying to refresh my memory. I haven't looked at the cartridge code in a little while. So this is where I create the cartridge. Here's where I initialize it. And I do have this load ROM here. What do I do again? So I open this file stream, and then I validate that the ROM has certain size and stuff. So which ROM am I loading again? I just want to double check that. I am loading this one called Scramble, which, let's go see what it looks like. Okay, so the cartridge size itself is 4096. So it's 4K, which is probably why my thing is that size, but the address space should be 32K. with no mirroring. So what this implies is that the program is accessing a memory address outside of the 4K cartridge ROM space. So either that's wrong, or because the cartridge was a 4K cart, if you were to access outside, it would wrap around and like basically modulo 4K, which is not impossible. I know when I was writing my NES emulator, there were, and it was known that there were ROMs, like NES games, that would address addresses, like they would address these kind of, out of bounds addresses, but it would work because it would, the address, there was like an address line that wasn't connected, and so it would effectively just ignore, let's say, the top bit or top couple of bits, and it would work. And, maybe they didn't realize, they didn't care, and it just, the game worked, and that's how it shipped. But then when you write an emulator, you end up finding these kind of like, quote unquote bugs in the original games. So that's a possibility. It's possible that this is valid, and we got to a point where it's trying to read outside of this 4K range, and it would have been okay on real hardware. The other possibility is that I have a bug somewhere in my CPU implementation, and we're like off into like invalid code here. Like we're not supposed to be executing this code. Like there's a whole bunch of possibilities. So what I want to do is I just want to see if I can identify where I'm at right now. Like F6B1. Let me just see, is this anywhere in the BIOS? Am I still in here, or have we jumped to the actual program, to the game itself? Because I mean, it looks like, right? It looks like we're maybe now in the game portion because of the fact that we're accessing memory in the cartridge memory map. So I just want to see F6B1. F6B3 is here. So are we, yeah, we're in here. We're inside this init music chunk, maybe? Init music DFT, CHK. These routines are responsible for filling the music work buffer while a sound is being made. It should be called once during each refresh cycle. If you want to start a new sound, then you must set this to 1 and point the U register to the sound block. If no sound is in progress, then it returns immediately, unless you called init music or init music DFT, which do not make this check. When a sound is in progress, this address will be set to 80. These routines process a single note at a time and calculate the amplitude and coarse fine-tuning values for the 3 sound channels. Okay, so we're trying to play a single note, most likely. And so it looks like we're not like in invalid memory. We're in the middle of this routine, which may be called either by the BIOS or by the game. So I'm not quite sure yet. So it seems a little bit strange that, okay, before I say anything, let me just take a look here. Yeah, so it wants to branch to F6EC. So is that the instruction I'm trying to disassemble? Instruction. Load B. So So that might be at FLLXCC. Ah, here we go. So this is the instruction we're at right now. We're at load B, vec music pointer, and we're trying to dereference this here, vec music pointer. And vec music pointer, so that's it. So this would be set by like the game. So it's very possible that now we're in Scramble, the game, and it's set the music pointer to an address in the cartridge. So if I just go to here, Vectrex include, music data pointer, so it would have set at this address in memory, C853, the address that we're probably right now trying to read to 7BED. So I wonder if actually we might be able to see where that value is being set. But one thing I noticed here is my load symbols failed. I think I loaded the wrong file, so we're not actually seeing the symbol. So let me just restart, correctly load symbols. It's this file. I'm just going to minimize it because I noticed that OBS CPU usage goes higher when I'm running when I'm outputting the debugger. Maybe I'm wrong. I don't know. Maybe it's just really slow. Another thing I might do is just disable the trace at some point. That for sure will make it go much faster. Okay, so here we are again. Okay, and now I actually have the symbols that I was missing before. So vec music work, vec music pointer. So I would like to see if I can see vec music pointer in here. I'm just gonna copy all of this, paste it here, so it's a little bit easier for me to search. And let's search backwards for vec music pointer. And it's not being found. It's kind of surprising. Just double check. We know we're doing a load B that is here. You know what I'm going to do is I'm going to put a breakpoint. I'm going to set a breakpoint here. And so before we execute the instruction, we'll just take a look at what memory looks like. Yeah, that could be useful. I'm going to have to check to see when we stop there. Okay, let's see. Oh, I guess my breakpoint's not hitting because we are... I would need to stop on the instruction before because I'm about to disassemble this instruction and I'm failing during the disassembly. It's also possible that I'm just doing this wrong. No. Maybe. Maybe. C853. Ah. Okay. Right, because that's right, this is an indirect instruction, as we see here, C853, and it went to read at the value exactly here at vec music pointer, C853, and it went and loaded the value there, and at that address in memory was this 7BED. So I wonder if I could find C853 in here. Aha. It's a bit surprising. Oh, look at that. Vec music pointer and channel A both double up as the same. Okay, this is why I'm not finding vec music pointer. Because when I built my map, I didn't realize that there were sometimes two symbols that map to the same address. Okay. All right, that makes more sense. So in my output, instead of showing up as vec music pointer, it's going to show up as vec expl channel A, so used by explosion sound bit. Okay. It's kind of not super awesome. I guess I could just maybe comment this out. But for now, what I'll do is I'll just look for this guy instead. So if we come back to here, and I mean this might actually be the place, store user stack pointer here. It's very close to the bottom here where we're breaking. So what's happening here? Saying store into user stack pointer value 53. So does this make sense? Okay, so this is the only place where it's interacting with this specific one. C851, C853. Storage for second music header word, twang table, whatever that means. And then C853 is the music data pointer. So it's saying stored a value in U. Okay, right. Stored a value in U at C853. Okay, because this is a direct pointer addressing mode. Okay, right. So what is the value in U? So here I'm actually showing that the value that's loaded into D is U++. 77, 79. Right, because plus here means increment. This actually means +2 in this assembly language. If you put a single plus, it's increment by 1. If you put 2 pluses, it's increment by 2. So what this implies is that actually, by the time we're here, 79 will have become 7B. ED7B, which is ED. No, sorry. ED. God, I suck at hex. Oh yeah, so it is ED7B. And then, there you go. And what we're seeing is we're seeing 7B ED because of the way it gets stored in memory. Sorry, I'm thinking because I'm wondering if, am I like just displaying the values incorrectly? Or am I, just let me double check this. So this again is indexed mode. Okay, so I know this is correct because I use this in the CPU. This is combining values in the most significant bit and least significant bit supposedly correctly. But the question is this ordering correct here? Like, what would it be if it really were ED79? Is that a valid range? Maybe that's what's going on here. You know what? I can cross-reference this with what the CPU does. Because again, we're in a debugger here, but there's a little bit of duality going on where the debugger has to do a little bit of the work that the CPU does, but I don't want to keep them, I don't want to have the CPU be aware of the debugger. So when I did my NES emulator, the CPU was aware of the debugger and kind of like pushed information to it, which made it more efficient, but it also made the design not great. The CPU was tightly coupled with the debugger, and I never liked that. So this time around, I made it so that the CPU has no idea that there's a debugger, but it means also that the debugger has to repeat some of the work that the CPU does internally because it doesn't have access to it. So there's a little bit of like copy paste to some degree, but it's not exactly the same. So in this case, it's indexed mode. Just want to see here, what am I doing in the equivalent case here? So post byte 2, read PC8, read PC8. So that just reads 2 consecutive bytes in memory, which is pretty much exactly what I'm doing here. And I'm combining the two, supposedly in the right order, unless that's wrong. Is the MSB first and then the LSB second in memory? I think it is. Let me double check. So let me go to indexed. Indexed addressing. 119. No, not finding it. Okay, yeah, this is the section. And I want to know for any one of the modes here that are dealing with 16-bit indexed addressing. So this is what again? Address, indirect only. There's a few examples of this. Plus or minus 15-bit offset. Okay, let's look for that one. Constant offset indexed. Specifies the 2 bytes following the post byte to be the 2's complement offset. It is a minimum 4-byte instruction. Okay, so it's not really talking about the ordering. And the 2's complement 16-bit offset is in the 2 bytes following the post byte. Sure. So here I think I can see the answer in this drawing, I believe. So it says indexed addressing mode, 16-bit offset example from Motorola. So let's see. Steps to determine effective address. 7077E. Right here we can see that most significant and least significant are in order. So it is big endian. So in general, that's what we tend to see, is that it's in the order that we expect. And then after completion, yeah, I mean, that's it. It's right here. So I'm not doing that wrong. Okay. Because I'm pretty convinced that that's not the problem. So then what I was seeing here, C853, we took those two and we read in memory two more bytes, the most significant and then the least significant, which provided this 7BED. Right. And if we come back in here, so that corresponds to the fact that by the time we get to this instruction where we store U has been incremented to that point. So what seems wrong here is it looks like I'm not displaying these values in the way I would expect. So maybe my comment display here is wrong. Which is kind of funny because this too is indexed addressing. It's one of the cases with the ++, which is up here somewhere. Here. This means I'm reading the value out of U. And just displaying it. There's something not right. What I'm going to do is I'm going to put a breakpoint when we reach this instruction here. And we'll take a look at what U looks like for real. Yeah. Those symbols. I'll just put a breakpoint on it and run until we get there. The joys of debugging CPUs. CPU implementations, anyway. just leave it open, whatever. I suspect that I'll get like 1,000-fold increase in speed if I stop using cout. I'm using cout here in just a few places, and I could just replace these with printf. I'm really not gaining anything, because in the end I'm always printing, pretty much I'm always printing strings, so I'm not even taking advantage at all of the formatting, like the overloaded part of cout, how you can pass it anything at all. It's always a string. So I think if I just change that to printf, it'll probably go like a lot faster. Okay, so we've hit our breakpoint, and I wanted to see here. Look at that. ED79. So that's really interesting. Okay, so there must be a problem. I think what's happening is I'm writing it and reading it back not the way I would expect. So yeah, let's step twice. We'll see what happens when we store u at this address, and we'll see what it looks like in memory. Maybe my store instruction isn't doing what it should. I mean, that seems kind of crazy, but and so there we go. So info reg. So when we were here, u was 7.9, now became 7b because of the plus plus. Twice, right? No, sorry, once, yeah. And then here, we're doing a load D with the value at u++. So whatever that was in memory, which I guess was this here. And now we want to store this value at C851. So that's not really helping me. Where's that? Oh, sorry, it's the next instruction that I cared about. The store u. Here we go. So we just stored the value of u at this address. So let's see if that's really the case. We're going to have to read 2 bytes to get back those values, the most significant and the least significant byte. So we'll say print here and here. So there's ED and 7B, exactly in that order. So what this is telling us then is that C853. Did I write it down before? Where were we? C853. C853 is this Vec music pointer. And when I'm reading from that Vec music pointer, I am reading it in the wrong order. Because I'm not getting this, I'm not getting back ED7B, I'm getting 7B ED, which is wrong. So that's the bug here. So Kevin asks, have you tried turning off sync with standard IO or something? I'm not sure what sync with standard IO is. console, not having the console sync with it. Let's see this link that Kevin is sharing. Sets whether the standard C++ streams are synchronized to the standard C streams after each input-output operation. It allows standard Cout to buffer the output. Oh, because by default it doesn't? In practice, this means that synchronized C++ streams are unbuffered, and each I/O operation on a C++ stream is immediately applied. So that's really interesting. You know, this is actually funny. I don't ever use C in, C out, like super rarely. You know, I learned them when I first learned C++ many years ago, because that's what they teach you. And then, I learned printf because it's blazing fast and easier to format your output. And that's all I ever use. And I don't know why I decided to use C out in this project. So like, I'm not even really comfortable with these standard streams. I really think I am going to just switch back to printf. Because again, I'm gaining nothing. But I could try this. So next time when I stop, I'll give this a whirl, see if it's faster. So I'll just keep this here. We'll see if that works. Thanks for sharing that. Okay, so yeah. Basically, I want to know why when we get down, so here's where the Vec music pointer, we know we're writing to there, and we know that when we get to this address here, F6EC, which we don't see here, we're going to be reading it. So and I think what's going to happen is, yeah, like when I run to there, I don't see what actually happens because it just ends up giving me the debug assertion, but that's okay. Yeah, there we go. I just wanted to double check. So what's happening here? I know what I want to do. I want to run until just before that instruction, and then I want to step inside here. So you know what, Kevin? I'll try this function here right away. We'll see if it's faster. So we want it to be false, right? Sync equals to true. We don't want it to sync. All right, so let's see. No, let's just run it. I can't tell if that was faster. Like, it was really weirdly slow at first, right? It's like so weird. Is it buffering or not? That's why we never use streams. So that behavior was like almost identical. I mean, a big part of this is OBS is a freaking huge CPU hog. It's crazy. It's like 60% of CPU usage right now. It's all right. Okay, so let's load my symbols. Set dude to FF. And let's put our breakpoint. I want it to stop just before so I could step. So yeah, Kevin, this doesn't seem to be any faster. Honestly, I don't even know if printf will make a difference. I honestly think what this is my CPU usage right now is like just show it really quickly there. It's like at 99%. So like OBS and the console are fighting for CPU. And I think we're just seeing the result of the switching between the two. I mean, maybe there's some buffering going on. I don't know. Pretty nuts. I'm gonna have to look into this off stream. I'll see if there's what people do. Maybe I gotta find a way to reduce OBS's CPU usage. Maybe there are a couple tricks to do that, and then because people use OBS to stream gaming, right? So, and my machine, I mean, it's not like the greatest machine ever, but I have. It's a Core i5 750 4-core at 2.67 gigahertz. Now all 4 cores are being maxed out, which is pretty crazy. And that could be because OBS is using multiple threads to do its compression and all that. So yeah, I'll take a look I'll take a look at that. Okay, I'll just minimize this because I actually do believe it goes faster. Because I guess what's happening is OBS sees, changes in the visual, and therefore it needs to compress more. Because I see that OBS CPU usage drops a good 10% or so when I don't have this visible. Okay. All right, so we're here at the breakpoint, and I wanted to set a breakpoint in my debugger code here for when I disassemble the next instruction. So where am I here? I'm right here at this get line. I'll just put my step. So here we go. I want to print this operation. I want to disassemble it. Okay, it's relative addressing. Branch instruction with 8 or 16-bit sign relative offset. Oh no, okay, sorry. This is not the one I'm worried about. Okay, this is just going to do the branch instruction. It's the one after the branch instruction that I care about. So let's step. Here we go. This is the one. This is the magic cookie right here. So let's see if we can figure this out. Step. Disassemble. It's not one of these. Index. Here we go. Okay, so here we go. So here's the 2 bytes that come after. And they point to C8 and 5.3 as expected. So C8, 5.3. And we support indirect, and we want to do an indirect lookup. And I'm reading at C8, 5.3 and C8, 5.3 plus 1, which gives me ED 7B. Which combined does the wrong thing? Oh my God. It's right in front of me. I'm passing LSB, MSB, but that's the wrong order. And there we have it. It should be MSB, and this should be LSB. So it's a debugger that was wrong. Let me see. In my CPU, do I must have this right in the CPU. I hope. Maybe I don't. Same bug. Okay, so the CPU would have done the wrong thing as well. Hey, Lucas's Plays. Cheers to you. So this is awesome. We fixed our bug. Cool. So we should be able to get further now. So let's see that happen. Load symbols. I'm so need to do something about having to retype this every single time. Lucas's Plays. I mean, this bug took like 30 minutes. It did indeed. Is that... are you implying when you say cheers and that you say it took 30 minutes, like that's a long time, or that you don't think it's a long time? Like, did it take long? I don't know. I don't know what you imply. Because, I mean, I don't think it took too long. Debugging these things can be tricky. What it's showing me is that I need a few more debugging tools. Like, I think I would have seen this faster if I was able... You know what, I'm just going to make a short list of a few things I would like to do. Like, I would really like for the debugger to... be able to print memory values and show like ASCII as well. Like more than one, you know. So right now I'm only printing one, but I like to print like a series of, like, given an address and perhaps you know, a count, show all values from that address up until the count in some kind of like nice formatted table or something. So Kevin says, some bugs cost millions. Yes, that's true. Lucas's Plays says, like those bugs, when you finally find a bug after more than 10 minutes, it feels great after deep research. Yes, yeah, totally. Yeah, like it does feel good to have found that one. In the end, I'm wondering, like, you know, how could I have avoided it? It's a human error bug, and yeah. Yeah, there's nothing much. I mean, you know, strongly type MSB versus LSB. Don't think that's really worth it. Maybe. Right, pound Microsoft. Hash Microsoft. So I'd like the debugger to print memory values. What else would I like? I would like to be able to have the debugger load like load a startup script, load and execute a startup script, which really would be trivial because in the end, because I'm using cin to read, like cin, I'm using getLine to read from standard input. I just need to like buffer in the standard input, and then it'll just kind of cycle through as if I type them. So that should be pretty easy. What else? What else would be useful? What else would have been useful while I was doing this? I think I thought of a third thing. Oh yeah, and the other thing I wanted to do was like speed up debugger trace output. Maybe try printf or look at OBS CPU usage. I don't know. Whatever that is. So. Okay. So now, what was the address that we were stuck at? Here we go. Copy. Let's set a breakpoint there, and let's run. So this makes more sense because I was wondering why it was trying to read in cartridge space that was, first of all, in cartridge space, but more importantly, outside the range of the cart itself, the 4K range. I mean, it's rare. Like I was talking about how some NES carts did read outside range, and like it worked because, you know, hardware-wise, it didn't matter. If the high bits are gone, it's as if you're just moduloing the value into range. But in truth, the games that would do these kind of illegal accesses were generally rare. And I mean, that kind of makes sense, right? So if you're writing a game for the NES, you're probably pretty careful about which addresses you're reading and writing to and from. So. Okay, so here we are. All right. So it's like the first time I actually printed disassembled instruction where I'm supposed to show, I didn't show it correctly here, I'm supposed to show the effective address in here. But we can see that it now is not crashing because it's correctly determining the effective address to be ED7B. So let me just see why the debugger didn't print that correctly. operands. Oh yeah, another really useful instruction that I need for my debugger is the ability to set the instruction pointer, which I cannot do right now, which basically means setting the PC. So let me add that to my list. Lucas's Plays writes, I wonder how a Windows tech feels when they find a bug, you know, more than 10 minutes. I'm not sure. Like, do you mean like a Windows tech, like someone who works at Windows? I mean, sorry, Microsoft? More than 10 minutes. Okay, so I want to set instruction pointer to address. Okay, so that will help me because like right now I'd like to move back, and I'm wondering why this operands did not have, like why did this not work? Operands should have been set. Oh, except I don't set it here. That must be why. This is where we must be going. I like just forgot this case completely. Okay. The reason why I didn't do this one is because I knew this was indirect. And that we would end up going into here. Right. But I had not actually put... So really I don't want to put operands here. I just want to put the effective address. That's it, right? Yeah. Sedated Snail says, some games did try to modify ROM as an anti-piracy emulation technique. Yeah. Right. Yeah, I mean, I can see what you mean. Like if you've got like some kind of you know, copier, or you know, like a Game Genie or something, writing to ROM might mess it up if it doesn't expect writes to those addresses or something. Lucas's Plays says, yes, and you know, software that is out for XY years already, and when they find a bug after all these years in some base code like kernel. Right. I mean, I'm not finding bugs in, you know, some old code from the Vectrex or anything, right? I mean, I'm just finding bugs in my own emulator. And, you know, I actually started this emulator like over a year ago, and I just put it down at one point after a couple of months. And recently decided to get back to it. Just had the urge, you know, to get back into working on something cool and on this emulator in particular, because I love the Vectrex. And also, you know, I've been kind of learning a lot of the modern C++ stuff, C++ 11, 14, 17 that's coming out. And it's fun, you know, it's fun to like, it's almost a new language now. So it's kind of fun to do something like this. So yeah, I just wanted to put here, I'm going to just do here like a formatted string again. And this will be the effective address, so I'll just put like this. Okay. So 46 EC. Load symbols. Set our dude register. Should be almost there. Okay. Yeah, this looks right. So it's funny, I think my breakpoint, oh yeah, that's right. Okay, that's it. I set a breakpoint here. We stop, we print it, but we don't actually execute the instruction just yet. So that's a bit strange. I think I have like a bit of a weirdness where yeah, this is not quite right. Normally I should break and not show the instruction here until I step. Because now I'm going to step and you're going to see the instruction twice printed out. Exactly. You see like here and here. So that's kind of weird. I'll fix that as well. Fix that breakpoint. Fix that breaking to debugger. Displays the instruction at that address. We stepping it, then displays it again. Sedated Snail, can I post a link to an article about GBA anti-emulation techniques? Pretty interesting stuff. Yeah, sure. Go ahead. I don't think I disabled link sharing or anything, so it's fine. You can go ahead and share links. Does sound interesting. Yeah. So memory mirroring is totally like it happens in the Vectrex as well. Yeah, exactly. The top bits are effectively masked out. So that's what I was saying before. So this is this actually used as a trick? What the classic Next series does with mirrored memory isn't particularly special. It copies code into main RAM and then jumps to one of these mirror addresses. This tends to confuse some emulators. Right. But it's never been a problem in MGBA due to how it implemented memory regions. However, this is by far the least troublesome trick the classic NES series pulls. Yeah, so I mean, I guess you can argue that it is a anti-piracy technique. I don't know. Anti-emulation, sure, but I mean, when these games were being written, were people really emulating them? You know, like the classic NES games, were people writing emulators? So I feel like, because they're rare, you know, I detect them in my NES emulator, and I've tried a bunch of games, and it's really rare. And usually when it happens, it's like one instruction, you know, that accesses this weird address that looks like it's out of bounds, but it's okay when it's mirrored. It just felt like more of a mistake than done on purpose, but maybe I'm wrong. I don't know. But these other ones look cool. Code in VRAM, yeah. Yeah, that's really cool. STM to DMA registers. Okay, I want to read this. This looks really interesting. Thanks for the share, Sedated Snail. It's really cool. So Sedated Snail says there were third-party consoles. Yes, that's true. That is absolutely true. So I guess what you're saying is that it would make third-party consoles more difficult. Like for third parties, more difficult to copy the hardware. They'd have to get it all right, including all the address lines and everything. Mainly arcade machines did it. Right, because people would copy boards and replace chips on boards and stuff. So to like make sure that didn't happen illegally, they would mess around with those addresses. I can understand it. These anti-piracy techniques of the time, a lot of them hardware-based. It makes sense. Just trying to remember where I was at. Oh yeah, that's right. So, great. So I continued, and now I hit the next unhandled op, which is add A. Cool. See, this is what I was expecting. I was expecting today to just keep hitting unhandled ops and implement them. Instead, I implemented NOP and then spent the rest of the time debugging why we were getting this invalid access. So now we're at add A, so that's cool. So let me just commit what I've got so far, at least take a look at what I've got so far. Right, so that's it, it's 2 fixes. Bunch of stuff here. Yeah, I think this didn't actually help, so I'm gonna remove this. Do a few check-ins. Implement NOP CPU instruction. I'll download that later. I guess I'll take all of this. And what I'll say here is fix indexed, indirect addressing, accessing bytes, no, combining bytes in the wrong order. Also fixed debugger accessing post bytes out of range. Just push that. So that's been pushed. So if you guys are like interested in looking at the code and following it, it's all on GitHub as I've written on my Twitch. Like if you read on the profile on Twitch, I give links to everything, including the GitHub site for this project. Which is here. So yeah, it's all here. It's on A. Majorano, my name, Vectrexy. I am using 2017 to build it, and I'm actually making use of some C++ 17 features. I have not tried building it in Clang or GCC, and I don't think it would be a problem building it there, especially since it's all console based right now. So, I mean, actually, that's not true. It probably won't build because I did not yet implement my platform specific stuff on the other platforms. Yeah, so I have an if-def win32. So there'll be like linker errors for missing implementations of some of these system functions. But probably like, yeah, set console control handler. So that's for being able to do Control-C to break into the debugger while it's running. And then set console color and get console color. These could just be no ops effectively. But yeah, so at some point I'll implement those for Linux, but not yet. So let's implement add a. Or add, just the add instruction. Because it was this one right here. So I actually already have subtract, but I never did add. Because I just implement them as they come. So opcode table. Let's take a look at what add looks like. Yeah, it's like pretty much like subtract in terms of the number of them. They're all on page 0. Yeah. Okay, so let's do this. I think the last time I did this, I just did search for add in the current document. Just like this. Copy that. Case all of this. Pop add. Okay. No. 0 Then I need to put that again. Something, break. Oh, these are not all adds. Okay, there's add with carry in here. Okay, so I didn't actually, you know what? Goodbye. Let's try it again. This time, oh, okay, that's why it's doing that, because I'm searching for add, but I need to search with match case. Okay, that's better. Case like that. Let's copy this. I love multi-column editing. It's pretty awesome. And then Clang format takes care of my formatting. Okay, cool. So I need to implement two versions of add, one for the 8-bit accumulators and one for the 16-bit registers, which looks like it's only D. It looks a lot. Let me see. Is that how subtract was? A, D. Yeah, it's exactly the same. This will be for add A and add B. So let's start with this one. Just want to bring up the doc for add. That's add with carry, add. Ah, so finally we get to set the half carry. That's cool. So far I haven't had to set half carry in any of the operations I've done. So it's an interesting concept. I never heard about a half carry before, but this CPU, apart from the normal carry, which is a carry that occurs when you add and a bit, like the most significant bit, would get shifted out. Here we have this concept of a half carry. So it's like you basically add, it's when you add, say, two 4-bit numbers and you want to know if like that caused a carry. And it actually supports that. That's kind of cool. This instruction, D is a 16-bit version. H is not affected for 16-bit, so it's really for only 8-bit. Okay. Okay, so I get my value here. from memory, add memory into register. So I'm supposed to take that and add it to the value of the register, into the register. So it's going to be reg plus equals to value, except that I need to know if a carry occurred. So what I can do is the simplest thing to do here is to do it in 16 bits. So actually I can store the value in 16-bit. I can also store my register in 16-bit. Then I don't know. Yeah. I'll just keep it like this. UN16 equal to value plus reg16. So let's set some flags. So how do I know? For this one, I don't know if I'm supposed to know if it was, sorry about that. For the half carry, what is it I'm looking for? Am I just looking to see if the bit is set in the result? I don't know. I need to look at what half carry is supposed to do. I mean, maybe my guess is that it's something like, you know, if like that. Maybe. Yeah, so this, same as this, 0 is the same. Let me just set the carry. Okay, so carry would be, I don't know if I prefer using a bit flag like this or just using my bits. Like here I'm looking at basically if bit 4 is not 0. And here I want to see if bit bit 8 is not 0. And now for overflow. Set if the operation caused an 8-bit 2's complement arithmetic overflow. Right. That means that not only is the bit Yeah. This is that case of when we need to know if the sign changed. So yeah, the idea here is if these are considered signed values, did the sign change as a result of adding? So what we need to know is, I think I already have code for this in here, but like if one is positive and the other is negative, like, hold on. Yeah, it's my code in subtract. Do I have this somewhere else? Here as well. But actually, this is what I care about. This can't be right. This is wrong. Yeah. I just realized I made a mistake here because I'm using this subtract template as this template function here for both the 8-bit and 16-bit case, but when I'm checking to set negative, I'm assuming it's the 16-bit case, which is completely incorrect. I'll fix that after. But for overflow, right, this is 8 here. I'll be right back. Okay. Try to wrap this up because I kind of have to go. So let's see. So yeah, so here basically what we want to check is if the input value and the result, sorry, what am I doing here? Starting to get a little tired. Start making mistakes. Okay, so it's the bitwise AND of the two values that we want to subtract in this case, and then we have the result. Okay. If we look at sign bits of A, B, R, then overflow set if 001 or 110. Okay. Basically, if we do the XOR of A, R, and B, well, A and let's say A and R, so the A is the input value. In this case, B is what value we want to subtract, and R is the result. In this case, we're adding because we're adding the ones complement, and we add 1 to make it the 2's complement. So we could just think of it as an addition. So if we do the XOR of A and R, so there's the input value and the result, and bitwise AND that with the XOR of A and B, and then we just check the 15th bit, which again is wrong for 8-bit subtract. What was I thinking when I did this? Guess I haven't hit a real 8-bit subtraction yet. But anyway, so we check the sign bit, and basically what we're checking, because we're checking just the sign bit, what we're saying is that there's overflow if the two values we're adding are 0, 0, but the result became 1, which means we added two positive numbers and became negative, or when we added two negative numbers and it became positive. So with this little XOR magic here, we're going to get a non-zero result in the case when this occurs, because 0 XOR 1 is 1, and 0 XOR 0 is 0, so that's 1. 1 XOR 0 is 1, and 1 XOR 1 is 0, so that's 1. And any other combination will always give us 0. Like if we have, 1, 1, 1, 1 XOR 1 is 0, and 1 XOR 1 is 0, so that's fine. Same thing, we have 0, 1, 1, so 0 XOR 1 is 1, 0 XOR 1 is 1, and which is 1. Is that wrong? This would be a positive plus a negative. Produce a negative. That's okay. 0 XOR 1. No. 0 XOR 1 is 1. And 0 XOR 1 is 1. I think I'm too tired to think through this right now, but it's right. Okay, so value sedated snail is less tired than I am, pointing out that 0 XOR 1 XOR 1 is equal to 0. But I'm not XORing twice, right? I'm ANDing in between. Anyway, let me just try to get this. Value is A. This is result. And B is my reg 16. Actually, I think what I really wanted was this to be reg 16. No, it's fine. So I think that's right. So you know what? I think I'm going to stop here. I'm feeling really tired. Get some good sleep. I'll get back to this, and I'll really just make sure this is all correct. I can also test it. I have a nice little emulator that I found for the CPU that I can write some code in and just make sure that it all works out. So yeah, I think I'm going to stop here. Thank you so much, guys, for hanging out and for the chat. Sedated Snail, Kevin, Lucas's Plays, and whoever else has been watching. So thanks a lot for hanging out, guys. And yeah, I might work on this off stream and just keep plugging away and see where I get to and continue next time. So thanks a lot, guys. See you soon.